Okay, so let's talk about linear regression. Now, as a subject, linear regression is over 200 years old and was first performed by two famous mathematicians, Legendre and Gauss. However, the basic concepts and techniques of linear regression are foundational to modern machine learning methods. Linear regression is just one type of regression, but all these other types of regressions have a lot in common. So we will use linear regression to explain some of these basic concepts. I want to acknowledge Dr. Murda Gaziaskar, who is the author of these slides, and let's go. So in this presentation, I'm just going to talk about univariate linear regression. I will give another video for gradient descent. Right now, univariate regression is used to model data. So we need to talk about how linear regression works as a model for data. And then cost function is important to determine how good the model is. If you remember when we talked about machine learning, there are three aspects to machine learning. Let's see, there's task, experience, and performance. So the cost function tells you the performance of the linear regression estimator. But the idea is to model data which can be used to predict data for future instances. And we'll see examples of this shortly. All right, so let's do some example. Suppose we want to predict housing prices. So we have some predict housing prices. This is my task. Now we need some experience or data. The data that we can obtain is for current houses, their size, the number of bedrooms, the number of bathrooms, garages. All of these are characteristics of houses that may affect the price. And then for houses that have recently sold, we can know the price that the house sold for. So this is the experience. This is what we will use in order to train our algorithm to predict housing prices. So that's what linear regression will do. Linear regression will take this experience or data and produce a model that can predict housing prices. And of course, we'll have to evaluate how good that model is. So let's do a simple case where we only look at the size of the house in square meters. So here's the size, and these are prices. Now these are prices in South African rand, so they may look a little bit strange to you depending on what country you're in. But bear with this data. And suppose we have not just 4, but we might have a large data set. So notice how this data is arranged. It's arranged so that each column has a significance. These are column vectors. Okay. And I could say that this is arranged in a matrix. But these are column vectors. We think of, and each data item can be considered as a row vector, right? This size and this price correspond to the same house. So each house gives me one row vector. Right? Now suppose that the data that I have can be plotted in this way. We can plot the size versus the price. For example, this represents one house that sold recently that has 300 square meters and roughly cost 3 million rand. This one up here, 600 square meters, and it cost 7 million rand. All right, now suppose I have a new house. Maybe the new house has a size of 250. What would the price be? What would I estimate the price to be? All right, so that's what regression will answer. It's going to give you a way to predict what the price of the next house you're looking at will sell at, even before it's sold. All right? So regression will predict a real valued, i.e. continuous output. That's what regression is about. You have continuous, or that's what linear regression is about. You have continuous data, your size, and you want to make a prediction of a continuous quantity. Now, there are other types of regression that don't have continuous inputs and continuous outputs, and we'll see that later. But this simple linear regression has continuous input and continuous outputs. Again, in this case, there's only one input, but later on we will see several inputs. Okay. So, and the general task of regression is to do a prediction like this. We're doing linear regression, but there are other types of regression: nonlinear regression, ridge regression, lasso regression, many, many different types of regression. And even some instances of deep learning can be considered as examples of a regression task, whenever you're trying to predict a continuous quantity. Now, this is supervised learning because in order to create the model, I need to have data where I know the right answer. I need to have data that includes the price in order to predict the price of new data. So you're given the right answer for the data points that you're using to train the algorithm. So this is one branch of supervised learning. The other branch is classification, where you're not trying to predict a value, but you're trying to find a category. For instance, you might want houses that are two-story or one-story or something like this, and you want to use the size data to predict some characteristic of the house. We'll see other examples of classification later. All right, so we see this diagram that we saw before. In the machine learning universe, our regression is over here. It's under supervised learning, and it's used for forecasting, prediction, which is the same thing, optimization, because you may want to set a system to have a certain level, and it will predict the level based on previous data. And then new insights, this is rather vague, but this is where supervised learning fits into the entire machine learning space. All right, let's go back. So here we have the same data table, but we need some mathematical notation. So this column vector is called x. That's the input variable. This column vector is called y. That's the output variable. Sometimes it's called the target. That's what we're trying to predict. M is the number of examples in the training set, so that would be the number of rows in this data set. And then xy is a specific sample in the training set. For instance, xi, yi would be the ith row here. Okay. So, sorry, x and y are used somewhat ambiguously. X can denote the entire vector, or x can sometimes denote one single instance of this vector. So you just need to understand from the context. But this is very clear. X sub I refers to the ith row and the first column. Yi also refers to the ith row and the second column. So for instance, x3 would be 155, y2 would be 1681. All right? Let's go on. All right. So within the context of machine learning in general, we've just seen the training data, and we will be getting down to the training the machine learning algorithm, and that we will use to get a model. So in this lecture, or in this video, we'll get down to here, to how a model or hypothesis is derived from training data. Okay. All right. So H is a mapping of values to of sizes to prices. That's what we can use to predict price if we're given the size. So the whole point of regression is to find this mapping H. So what does H look like in this case? All right. So here's our data that we have already. And H, for linear regression, H can be represented as a line through the data. Now you can see that this line captures the general trend of the data. So that's what we want. We want a line that captures the general trend. And the intercept of the y-axis is called theta 0. And the slope or gradient is called theta 1. If you remember, slope is the rise over the run. So in this case, it looks like the rise is about 1/3 of the run. So this would have slope approximately 1/3. So my H, which maps sizes to prices, is going to be a line with this intercept, theta 0, and this slope, theta 1. So this is a standard representation of a line with intercept and slope. In fact, this is called slope-intercept form. So again, gradient and slope are the same thing. Now, we can try different hypotheses. We can try different linear functions with different theta 0s and different theta 1s. So you can see the different lists here. So this is like the story. There's a fairy tale in US that we call the Three Bears, and the mama bear, papa bear, and baby bear, and they each have their own porridge, and Goldilocks comes in and tries the three porridges, and one's too big, one's too hot, one's too cold, and one is just right. So what you want to do is find the line that is going to be the right intercept and the right slope. Okay. All right, so here I have an intercept here. This slope is definitely too small. We need a more positive slope to capture this data. Okay. Now this slope is maybe too big, right? And I think the intercept is too small. So this is this one. Neither one of these is so good. Now this one also, the intercept seems to be too big, but the slope seems about right. Now, when you're doing this in practice, you don't want to keep trying different lines and just use trial and error. You want a systematic way of determining the best line. All right. So here we have some data, as we've seen before, and here are some different lines. Okay. Now, each one of these different lines that we saw up here has a different theta 0 and a different theta 1. So let's see. It turns out that the best fit, and we'll see how you get this best fit, has theta 0 equals 1740 and theta 1 equals 8.4. Well, you can see theta 0 is right here, and that value is actually 1740. You can see it's between 1,000 and 2,000. And the slope here is 8.4. You can see that because it goes, say, from roughly here, this point is 600 and 700, and then to down here, which is roughly 0 and 200. So it basically goes up 500 in an interval of 600. So if you work that out, that's roughly 8.4 if you take the rise divided by the run. So given those values, I want to predict a particular value. Okay. This H0 represents the prediction of the price given a house size of 320. So what do? To get this prediction, you go down to the x-axis, locate the size, and then find the point on the line that corresponds to that point on the x-axis. So it's going to be up here. You see, 320, we go up here, and then the prediction is going to be right here. I haven't shown the line yet, but given this formula for theta 0 and theta 1, right? Theta 0 is the intercept, theta 1 is the slope. I plug in my value of size, and I get this prediction. And there we have it. Now, if I was going to predict another value, see if you can see where that point would be. It's the same process, right? I just choose a different point on the x-axis, find the corresponding point on the line, and I find the corresponding point on the line by using my formula, theta 0 plus theta 1x, and that will give me the y value. Okay. Here's another one, so you can see H650 is going to be the same result. I mean, the same process. Okay, so the summary, we need to fit a line h theta onto the housing data. Linear regression means we're fitting a line. The line is determined by two parameters, theta 0 the intercept and theta 1 the slope. Once we have an appropriate line, we can make price predictions on any unknown values in the future. In the previous slide, we made price predictions for 3 different sizes. Now, I can't tell how accurate those were, but those were predictions, and they seem to be reasonable predictions based on the data. All right, the values of theta 0 and theta 1 will determine how well the line fits the training data. So, very important, the perimeter values also determine how accurate future price predictions based on size may be. Okay. So theta 1 and theta 0 determines how well the line fits the data you have, and presumably, if the line fits the data you have well, it will also fit well future data that you may have. Now that's an assumption. The assumption is that future data will resemble current data. Okay. So this is, in a nutshell, is a univariate linear regression problem. Has these characteristics. So the big question is, how do we determine the best theta 0 and theta 1 to use? So I think this is a good place to stop. We will continue in the next video.